Let's continue with the next lecture where we're going to expand upon the idea of expansion processes for ideal gases. This continues Chapter 2, Section 2.7, where we're not only looking at ideal gases but also the ideal processes associated with them. And when I say an ideal process, I really mean effectively a reversible process. This would be the limit to which we could take a closed system and yield work from them. Both of these processes, isothermal and adiabatic, are going to be called polytropic processes, and we described that in the last lecture. At least we expressed the term, and we're going to explore what it actually means inside of this lecture. Looking ahead, why we're doing this exploration of polytropic processes is the two are pressure volume work scenarios, PV work scenarios, for ideal gases, and they make up the foundation for ideal thermodynamic cycles, or the Carnot cycle. I want to remind you also that an expansion process is what we will explore and what the textbook explores, and that is just the opposite in direction of a compression process. So if we have expansion processes and we apply a negative sign to them, we are actually just, it's a very simple matter to describe, which is why you're only seeing expansion processes explained in the textbook. The two closed system processes are going to be the expansion of an ideal gas that is isothermal in nature, and the expansion of an ideal gas that is adiabatic and that has constant heat capacitance at constant pressure. Constant pressure would be an isobaric system. Adiabatic is where dQ is going to be equal to 0. The isothermal process, because we're talking about an ideal gas and there's no change in temperature, and temperature is the only property that changes the internal energy of an ideal gas, so we have a change in internal energy equal to 0 in an isothermal process for this ideal gas and ideal process that we're describing. Let's go and talk about the first one, the isothermal process. We've already explained this a bit, but here's where we come into the idea of a polytropic process. So something is polytropic if I can express pressure and volume being where volume is raised to the gamma, and we'll explain what gamma will be later, such that the answer is a constant. Okay, you'll see that on page 95 in the summary discussion of these two processes. But polytropic is a process that has the form PV gamma equal to a constant. In the case of an isothermal expansion, PV is going to be raised to the first power, and it's going to be equal to nRT. That is the equation of state for the ideal gas system. So N is going to be constant because it's a closed system. R is a constant because it's the ideal gas constant, and T is going to be constant because it's an isothermal process. So collectively, it's PV is equal to a constant, where gamma this time is equal to 1. I'm going to review the setup that we did last lecture, which is to take two different equations. The first is that the change in internal energy is going to be 0 for an ideal gas when it's isothermal process. And the second is that the work function can be described as nRT times the natural log of the end condition, the pressure at state 2, over the initial condition, the pressure at state 1, and that's equation 2.38. I'm going to take both of those equations, 1 and 2, and I'm going to insert them into the different parts of my equation for the first law for closed systems. This is an equation where we're only describing mechanical work, W, heat, Q, and the change in internal energy. All energy that is work in this system is going to be from heat transfer from the surroundings, because delta U is already equal to 0, which means that Q is going to be equal to negative W, or W is equal to negative Q. So all of the energy that is work, W, is going to come from heat transfer from the surroundings. So we combine those together, and you're going to see that I've got Q is equal to minus nRT natural log of P2 over P1, which is equation 2.39. Because we're using these natural logs quite often, I want to at least raise the question again for you to think about what happens to the ratio if I change the sign from a negative natural log to a positive natural log. Right? The idea is that I will have a negative natural log as P2 over P1. If I were to change the sign, I would have natural log of P1 over P2. Just something to keep in mind, just basic math of logarithms to be aware of. If I look at the sign analysis, and again, this is a review of last lecture, I find that delta U is going to be 0. Q is going to be a value that's positive. That's energy coming into the system from the surroundings. And W is going to be negative. That's going to be the work leaving the system. If I were to look at a compression system, I'm effectively changing the sign, right? Because I was just saying earlier that compression is just changing the sign, so I would have that natural log of P1 over P2. At this point, I'm not looking too closely about which state is which, but equivalence is just a matter of a change in sign. All right. Now the big one that we need to discuss today is an expansion that is in a constant pressure system. It will have a constant heat capacitance, and the system or the process is going to be an adiabatic process. And what's interesting is that this will describe a PV gamma, PV raised to the gamma, equal to a constant scenario. Only the gamma here is going to be a coefficient K that is going to be equal to the ratio of the constant pressure heat capacity over the constant volume heat capacity. We've already seen in our reading and in our earlier notes that the constant pressure heat capacity will always be a higher value numerically than the constant volume heat capacity, which means that gamma, or K in this term, will always be greater than 1 when we're looking at our analyses. So let's start with equation 2.40, where we're going to put Q in differential form, and we're going to describe dQ relative to du, and we already know that dW is going to be minus pdV. That's going to be equal to 0. You're going to see that du describes my internal energy, pdV describes flow work, and so what we're actually describing is enthalpy. It's a constant pressure system, so it should be no surprise that we're bringing in a pressure-related energy term describing the system, and that's enthalpy. If I integrate that, I'm going to have Q is equal to 0, and we would then have dH equal to Q. Okay? Now, when I say adiabatic, I'm just reminding everyone that adiabatic means that heat is 0, or the transfer of energy that is heat across the boundary is going to be 0. There will be no energy transferred across the boundary as heat. So the second equation, 241, is going to be my definition for du, or the differential form of the change in internal energy of the system. That's going to be N times the constant volume heat capacity dt. It's just the way that we define du. So we use that definition, and we will pop that N CV dt into our next equation when we describe the first law. So work, again, is going to be with 2.42 minus PdV. You're seeing it up in equation 1 already. If I rearrange these, and you see equation 1, and what I'm doing is I'm going to rearrange equation 1, and I'm going to put the, I know that dq is equal to 0, and so I'm going to set my state function on the left side of the equation, my path function on the right side of the equation, and so I have du is equal to dw. State function on the left side, just as we've always done, path function on the right side. I'm then going to substitute for du and dw, and then I have equation 2.43, where I've just taken the equation 2 for du, substituted that in, equation 3 for dw, and substituted that in on the right. What this means is that if I have an isobaric expansion process that is adiabatic in nature, the energy for work is going to come from the internal energy of the gas inside the system, right? So if I suck internal energy out of the gas, I will change the temperature of that ideal gas, because there's a direct relationship between the internal energy and the temperature of the system for an ideal gas. So all the energy for work in an adiabatic process comes from a change in the internal energy of the gas. Now, let's look at the ideal gas equation of state. You see that EOS? That means equation of state in the notes and throughout. If I use the ideal gas equation of state, I can express temperature as PV over NR. I'm going to then differentiate temperature. I'm going to have dT, and then I'm going to differentiate P and V in parts on the right-hand side. So you'll see dPV, or more appropriately PdV, plus VdP plus PdV. So I've differentiated both P and V in parts, and that's divided by N over R. N and R are both constants because this is a closed system, so there's no mass transfer across the boundary. N is constant, and R is the ideal gas constant. Now I'm going to take dt, I'm going to solve dt and insert it into equation 2.43, which you will see on page 93 for the N times CV times dt. So I'm going to try to insert my pressure-volume relationships instead of a temperature relationship. This is takes a bit of work to get through, so we're going to work through those equations and show how we get there, because inside of the textbook it's not very clear. So how do we do that? We're going to take CV, and we're going to, because we have N times CV times dt, and we're going to take this equation for dt that you see at the top of the screen, and we're going to combine it with equation 2.43. So we're going to have CV over R VdP. That's that first term. And we're going to have CV over R times PdV. That's the second term. The N is gone from the dt term because there's a numerator and a denominator for N, and they cancel out. The R will remain in both of them. Now, each one of those is going to be equal to PdV because we've just solved or inserted dt in for the left-hand side, the state energy change side of the equation, and we've left PdV on the right for the path function. That's equation 2.43. This might be a good time to pull out your book and take a look at these two to see where we're going. Now I'm going to bring my CV over R PdV term over to the right side. And so I'm going to have all of my PdV terms on the right-hand side of the equation, and that's what you see in the next line. I'm going to further move my gas constant over from the left side of the equation to the right, and they will cancel each other out. The numerator and the denominator R will cancel out, which will leave me with CV times VdP is equal to minus CV plus R times PDV. Now, why do we have that? What could we use to solve this if we have CV plus R? What do we know about an ideal gas and the constant volume heat capacity versus the constant pressure heat capacity? Well, we've already learned that the constant pressure heat capacity is larger than the constant volume heat capacity. So CV plus R for an ideal gas model is going to be equal to CP, and that's why you're seeing the substitute for minus CP instead of CV plus R. And that's going to be equation 2.45. We take a big breath of relief because that was doing some major gymnastics of moving mathematical variables around, at least for this class. And we see that we have a relationship between constant volume heat capacity and constant pressure heat capacity on the left-hand side of the equation and on the right-hand side of the equation. What I'd like to do is to separate my variables in equation 2.45 so that I have all the volume terms on one side and all the pressure terms on the other side. That brings us to equation 2.46. So I have dV over d, or 1 over v times dv, and 1 over p times dp on the right-hand side of the equation, which leaves us with a ratio of Cp over v, or K. That's what brings us to a polytropic definition. So we have PV to the K equal to a constant, where in this case K is a value greater than 1 because Cp is always going to be a value greater than CV for an ideal gas. This would be a good time to pause, go back, look at this, and think about where we've gone through in these equations. Mainly, it would be a good time to also look at the way that we've differentiated temperature and then subsequently differentiated the parts of pressure and volume to finally arrive at this relationship. I would describe this as a very good practice piece to look through. When we then integrate equation 2.46, and we'll use the coefficient Cp over Cv for our adiabatic expansion or contraction, right? I want to remind you that when we integrate, we're basically integrating 1 over the variable, which again brings us to a natural log of the final state over the initial state. This is just the basic formulation of that equation, or that integration. And for us, it's going to be minus k times the natural log of v2 over v1 is going to be equal to the natural log of p2 over p1. That's the integrated form. That's the form that we want to use, but that's also why we started with the differential form first. It was actually easier for us in the adiabatic process to begin with the differential form of the equation and then only integrate it once we had our variables separated to be able to look clearly at the initial and final states. I can rewrite the natural log of v2 over v1 times minus k. Using basic logarithmic manipulation, it'll be the natural log of v2 over v1 raised to the minus k. And similarly, that's equivalent to the natural log of v1 over v2 raised to the k. Might as well become familiar with this because a lot of these basic manipulations are going to be coming up over and over again in thermodynamics. This is a skill development that I want you to have in your understanding by the time you leave the class. So now I can take this and rewrite it as the natural log of P1 V1 raised to the k, where the volume is raised to the k, is going to be equal to the natural log of P2 V2, where V2 is raised to the k. Or, once again, PV to the k is equal to a constant. Another way that we would write this is that pressure is going to be that constant times V to the minus K. And yeah, we've really come a long way. We've done a lot of manipulation of equations. Why did we do this? Why did we manipulate these equations? Let's go back to the work part of an adiabatic process and see how this effort has played out. So work itself, we already know in the integrated form, is going to be minus the integral of p dv. And if I do that for two distinct changes of state, I can replace p with constant times v to the minus k. And you can see that relationship. But then I can go further and say that that integral can be evaluated as a constant over k minus 1 times the differences in the inverse k. Oops. And that should be a p right there. So p1 v1 to the k times v to the v1 to the 1 minus k. It's just showing you how we're manipulating the equations to get the values that we were looking for in the first place. Work is going to be 1 over k minus 1 times p2 v2 minus p1 v1. And how we got there is because of these different relations and substitutions. But if I have a system, I'm not measuring P and V, I'm only measuring temperature, the temperature in state 1 and the temperature in state 2. How do I use that? Well, I use the ideal gas equation of state, and I relate temperature to pressure. I'm doing the very basic code breaking that we talk about in thermodynamics. I am converting PV terms into temperature terms, and you're seeing it right there. And that's going to be the useful form that we will use in answering our thermodynamic questions. So the side note here, I'm just making a couple of relationships explicit for you. You're welcome to pause and take a look at this and see how we were manipulating equations. Some of you will want to know exactly how these equations were manipulated. Others will be quite content with just work is equal to nr over k minus 1, t2 minus t1. All right, now we've got something we can use. So let's apply the first law again in integrated form. We know that q goes to 0, and so dq is going to be equal to w. Because du is equal to w, I will be able to put in my representative values for w for du. So you see nr over k minus 1 times t2 minus t1. That is the answer for du. It's also the answer for w, for the work of the system, which is why we will say that the internal energy change is what drives the work in an adiabatic system. If I do the analysis here, I find out that du is positive, q is 0, and work would be positive. All right. So the last thing I want to do is to review the polytropic processes, make a comparison of the two in a table. You'll see it in table 2.2 on page 95, but I'm going to review it right here. Again, I'm going to have a change in internal energy term, a path function for the integrated form of heat, Q, a path function for the integrated form of work, W, and I know that both of these processes, isothermal expansion and adiabatic expansion, are going to be using ideal gases, and they're ideal processes that follow the form PV gamma equal to a constant. Let's look first at the isothermal process. In an isothermal process, delta U is equal to 0. My heat is the opposite sign of my work, because the work will be the important part of the equation, and what we use the work for, how do we get the work, is from the energy that's coming in from the surroundings or going out of the surroundings. The adiabatic process, Q is equal to 0. But because of our first law analysis, and because of our lengthy analysis of gas behavior and relationships through equations of state, both du and W are the same equation. nR over K minus 1 times T2 minus T1, where K is the ratio of heat capacities for an ideal gas. Each case, the isothermal and the adiabatic, represents an ideal limit, right? The ideal limit for the isothermal system is where all work comes from, all the work energy comes from the heat energy from the surroundings. Whereas the adiabatic system, all of the work is derived from the internal energy of the gases. So next lecture, we will be taking this to the next level. We will be opening the system and describing process equipment. And of course, we will end the class with quiz 2. Thank you for your time.